Read each statement below carefully and state with reasons if it is true or false. A. During rolling, the force of friction acts in the same direction as the direction of motion of the central mass of the body. B. The instantaneous speed of the point of contact during rolling is 0. C. The instantaneous acceleration of the point of contact during rolling is 0. D. For perfect rolling motion, work done against friction is 0. E. A wheel moving down a perfectly frictionless inclined plane will undergo slipping, not rolling motion. Now let us give an answer to part A. For that we consider the following figures. A part. During rolling, the force of friction acts in the same direction as the direction of motion of the central mass of the body. We have to say whether it is true or false. It is false. Why it is false? Rolling may occur in two different ways. One can be perfect rolling, and in other cases there can be an external force acting on the rolling body. Let us consider the case in which an external force F external acts on the body. Then there are two possibilities for the point of action of the forces with respect to the distance from the ground. If the distance to the point where the external force acts is greater than the radius of the rolling body, that means for h greater than capital R, the force of friction will be in the forward direction. That means in the direction of motion of the center of mass, that is towards right. Why? Here the external force applied tends to rotate the body in the clockwise sense, and so friction force acts in the direction of motion, that means towards right, as in figure 1. And if the external force applied is at a point which is at a distance small h from the floor, where h is less than capital R, then there is a tendency to rotate the body in the anti-clockwise sense. In that case, the force of friction will be opposite to the direction of motion of the center of mass. That means the force of friction will be towards left, as in figure 2. Now, the other case is that if there is no external force acting on the body and if the body undergoes perfect rolling, the condition for perfect rolling is that the velocity of the center of mass VCM equals R into omega. So the center of mass of the body moves towards right with the velocity VCM. This velocity is shared by all points on the body, and hence the point A, which is in contact with the surface, also shares this velocity in the direction towards right as shown in figure. At the same time, due to rotation, this point of contact A will be having an equal velocity R omega in the opposite direction. So due to these two velocities, the instantaneous velocity of the point of contact A will be 0. That means V instantaneous is equal to 0. And also in this perfect rolling case, the force of friction F becomes 0. So the force of friction becomes 0 here. So if there is an external force, we cannot definitely say the direction of friction. The friction can be towards left or towards right, as given by figures 1 and 2. At the same time, if the rolling is perfect, then the frictional force reduced to 0. So in all these cases, it is clear that we cannot say the direction of the force of friction. So the first one is false. Now B part. The incident speed of the point of contact during rolling is 0. This is clear from the third diagram. That means when the body is undergoing perfect rolling, then the velocity of the center of mass of the body VCM is given by VCM equals R omega. This velocity is also shared by the point of contact A, and so it has a velocity towards right, VCM towards right, as in figure 3. Meanwhile, it has an equal velocity r omega due to rotation motion towards left. So the instantaneous speed of the point of contact A will be 0. So we see that C part, the instantaneous speed of the point of contact during rolling is equal to 0. So this is true. Now C part. The instantaneous acceleration of the point of contact during rolling is 0. This is false. Why? Just after the point of contact A is in contact with the floor, it begins to move up, and as a result there will be a change in velocity for the contact point A. Hence there will be a rate of change of velocity or acceleration. That means the acceleration of the point of contact during rolling is not equal to 0. So A not equal to 0. Now D part. For perfect rolling motion, work done against friction is 0. We have already seen that this is true. We have already seen that for perfect rolling, the condition is Vcm equals r omega. The center of mass moves with the velocity given by r omega, and the friction force just after perfect rolling begins is equal to 0. F is equal to 0. Hence work done against friction is 0 for perfect rolling. Now E part. A wheel moving down a perfectly frictionless inclined plane will undergo slipping, not rolling motion. This is true. Why this is true? For rotation, frictional torque is required. For rotation, friction torque is required. So this is true. Okay. Separation of motion of a system of particles into motion of the center of mass and motion about the center of mass. A part show Pi vector equals Pi dash vector plus Mi into capital V vector, where Pi vector is the momentum of the ith particle of mass Mi, and Pi dash vector equals Mi into Vi dash vector. Note, Vi dash vector is the velocity of the ith particle relative to the center of mass. Also prove using the definition of the center of mass, sigma Pi dash vector equals 0. B. Show capital K equals capital K dash plus half capital M into capital V square, where K is the total kinetic energy of the system of particles. K dash is the total kinetic energy of the system when the particle velocities are taken with respect to the center of mass, and capital M V square by 2 is the kinetic energy of the translation of the system as a whole, that is the center of mass motion of the system. The result has been used in section 740. C. Show capital vector equals capital dash vector plus capital R vector cross capital M into capital V vector, where capital dash vector equals sigma Ri dash vector cross Pi dash vector is the angular moment of the system about the center of mass with the velocities taken related to the center of mass. Remember, Ri dash vector equals Ri vector minus capital R vector. Rest of the notation is the standard notation used in the chapter. Note, capital dash vector and capital M into capital R vector cross capital V vector can be said to be angular momenta respectively about and of the center of mass of the system of particles. D part. Show D capital dash vector by dt equals sigma Ri dash vector cross dp dash vector by dt. Further show that dl dash vector by dt equals tau dash external vector, where Tau dash external vector is the sum of all external torques acting on the system about the center of mass. Hint, use the definition of center of mass and the third law of motion. Assume the internal forces between two particles act along the line joining the particles. To do this lengthy problem, let us divide the problem into A part, B part, C part and D part separately due to lack of space. For that, let us draw a figure. In the figure, Cm is the center of mass of a body and capital R vector is its position vector with respect to origin O. Mi is the mass of a small particle with a position vector Ri dash vector with respect to center of mass and with a position vector Ri vector with respect to the origin O. Now let us consider the problem separately for A part, B part, C part and D part. We have to show that Pi vector, the question is to be corrected. Pi vector is the left hand side, that is equal to Pi dash vector plus small mi capital V vector. To prove this from figure, we can write Ri dash vector equals Ri vector minus capital R vector. Now differentiating with respect to time, we get derivative of Ri dash vector. Derivative of Ri dash vector means Vi dash vector. Similarly, that of Ri vector is Vi vector and that of capital R vector is capital V vector. Now multiplying this equation throughout with the mass of the particle small mi, multiplying with the mi, we get mi Vi dash vector equals mi Vi vector minus mi V vector. Now the left hand side is the momentum of the ith particle with respect to the center of mass. So it can be written as Pi dash vector, that's equal to mi Vi vector means the momentum with respect to the origin O. It can be written as Pi vector minus mi capital V vector. This is relation number 1. Now we can write Pi vector as Pi dash vector plus mi into capital V vector. This is to be proved. Now we have to show that sigma Pi dash vector equals 0. For that, let us consider relation 1. So from 1 we get sigma Pi dash vector equals sigma Pi vector minus sigma mi V vector. This is equal to sigma Pi vector means sum of the moment of all the particles of the body with respect to the origin. So it is the momentum P vector of the body with respect to the origin minus sigma mi means the mass of the body, that into V vector. That means this is P vector minus m into V vector means the momentum of the body with respect to the origin or P vector itself. So that is equal to 0. Thus we have proved that sigma Pi dash vector equals 0. Okay. Now let us do B part of the problem. In B part, we have to find the relation among kinetic energies with respect to the center of mass and with respect to the origin, and show that K equals K dash plus half mv square. For that, let us consider the equation for the velocity. Velocity Vi dash vector equals Vi vector minus capital V vector. Now taking dot product with itself, this equation can be written in the form Vi dash vector dot Vi dash vector equals Vi vector minus V vector dot Vi vector minus V vector. This is equal to Vi vector dot Vi vector minus Vi vector dot V vector minus V vector dot Vi vector plus capital V vector dot capital V vector. Now this can be written as Vi dash vector dot Vi dash vector means Vi dash whole square. This is equal to Vi vector dot Vi vector means Vi square minus 2 Vi vector dot V vector plus V square. Now multiplying throughout with multiplying the equation with half Mi, where Mi is the mass of the ith particle, we get half Mi Vi dash square equals half Mi Vi square minus Mi Vi vector dot V vector plus half Mi V square. Now taking sigma on both sides, we get sigma half Mi Vi dash square equals sigma half Mi Vi square minus sigma Mi Vi vector, this can be put within bracket, dot V vector plus half sigma Mi into V square. This left hand side represents the total kinetic energy of all the particles of the body with respect to the center of mass, or it is K dash, the kinetic energy of the body with respect to the center of mass. That's equal to sigma half Mi Vi square means the kinetic energy of all the particles of the body with respect to the origin O. It is the kinetic energy of the body with respect to the origin, that is K. So K minus this means sum of all the momenta of all the particles of the body. It is equal to the total moment of the body, or it is capital M, the mass of the body, into capital V vector dot V vector plus half sigma Mi means capital M square. Now this is equal to K minus MV square plus half MV square, or this is equal to K minus half MV square. Writing the expression for K, we get K is equal to K dash plus half MV square. Okay. Now let us do C part. Show capital vector equals capital dash vector plus capital R vector cross capital M into V vector, where capital L dash vector equals sigma Ra dash vector cross Pi dash vector is the angular momentum of the system about the center of mass with velocities taken relative to the center of mass. Remember, Ra dash vector equals Ra vector minus capital R vector. The rest of the notation is the standard notation used in the chapter. Not L dash vector and capital M capital R vector cross capital V vector can be said to be angular momenta respectively about and of the center of mass of the system of particles. Let us write down Li dash vector. Li dash vector means the angular moment of the ith particle with respect to the center of mass. So it is Ri dash vector cross Pi dash vector. This is equal to Ri dash vector means Ri vector minus capital R vector, and Pi dash vector means Pi vector minus small mi into capital V vector. So this is equal to small Ri vector cross Pi vector minus mi Ri vector cross V vector minus capital R vector cross Pi vector plus capital R vector cross mi capital V vector. This is equal to, this is the first term Ri vector cross Pi vector means Li vector, the angular moment of the ith particle with respect to the origin, minus mi Ri vector cross capital V vector minus R vector cross Pi vector plus R vector cross mi capital V vector. Now taking sigma on either side of the equation, we can write sigma Li dash vector equals sigma Li vector minus sigma mi Ri vector cross capital V vector minus R vector cross sigma Pi vector plus R vector cross sigma mi into V vector. Now sigma Li dash vector is the sum of all the angular momenta of all the particles of the body with respect to the center of mass. So it is the angular momentum L dash vector of the body with respect to the center of mass, and this is equal to sigma Li vector means the angular momentum of the body with respect to the origin minus sigma mi Ri vector means capital M into R vector. Why? We have the relation for capital R vector as sigma mi Ri vector divided by capital M, the mass of the body. So this cross V vector minus R vector cross sigma Pi vector means the total momentum of the body with respect to the origin. That means it is M into capital V vector plus capital R vector cross sigma mi means capital M, and so M into capital V vector. We can simplify this. This is equal to L vector minus R vector cross MV vector minus R vector cross MV vector plus R vector cross MV vector. This is equal to L vector minus R vector cross MV vector. Therefore, we get the expression for L vector as L vector equals L dash vector plus R vector cross capital M V vector. Okay. Now let us do the D part. We have Li dash vector. It is the angular moment of the ith particle with respect to the center of mass. It is given by Ri dash vector cross Pi dash vector. Now differentiating this with respect to time, we get dli dash vector by dt equals, applying product rule, we get Ri dash vector cross dpi dash vector by dt plus dri dash vector by dt cross pi dash vector. This is equal to Ri dash vector cross dpi dash vector by dt plus dri dash vector by dt means this is vi dash vector cross pi dash vector means mi into vi dash vector. This is equal to Ri dash vector cross dpi dash vector by dt plus here there is a term vi dash vector cross vi dash vector, it is 0. So this term will be 0. So we get this as this is equal to Ri dash vector cross dpi dash vector by dt. Taking sigma notation on both sides, we get sigma dli dash vector by dt equals sigma Ri dash vector cross dpi dash vector by dt. This means that sigma li dash vector by dt means sum of the rate of change of all the angular moment of all the particles of the body, or it is the rate of change of the angular momentum of the body with respect to the center of mass. So this means dl dash vector by dt equals sigma Ri dash vector cross dpi dash vector by dt. So first one is proved. Now we have to show that dl dash vector by dt equals tau dash external vector. We have shown that dl dash vector by dt equals sigma Ri dash vector cross dpi dash vector by dt. This is equal to sigma Ri dash vector cross dpi dash vector by dt means the force, or it is the force acting on the ith particle, or it is the external force acting on the ith particle, since all the internal forces cancel out. So sigma Ri dash vector cross Fi dash external dash vector. This is equal to sigma torque, external torque acting on the ith particle with respect to the center of mass. So that's equal to the total external torque acting on the body with respect to the center of mass, that is tau external dash. So we have proved that dl dash vector by dt equals tau external dash vector. Okay.